record the lecture also, just in case. So we want to also see, first of all, why do functional equations in? So what are we trying to do? What are we trying to do when we solve functional equation? I mean, of course, from the tricks perspective, there are some tricks we are trying to apply, but what is it that we're trying to understand finally?
Yeah,
Yeah, so can you say?
it's like trying. Usually, it's trying to find functions that functions from a given equation.
Very good. Yeah, basically that's it, right? Yeah, find the function from equation. Okay, so that's good. But then the other thing is that why do functional equations pop up so often? I mean, from the context's perspective, because they give it in the contests. But why do they in general pop up if you feel that is the case? Then why do they pop up so often? These are the questions I ask myself. Yeah.
Yeah,
Yes. Why do you think?
I'm unaware of that.
Okay, yeah. But you must have seen functions being defined by equations very often rather than, defined explicitly, right?
Yeah,
So usually defined via equations. Why? Because you see, usually, so this I'll just say in words, usually functions come about from some kind of process, right? Some kind of algorithm is running, yeah, and you study the nature of that algorithm and you connect the various, so you see the nature of the function and you try to form an equation from that nature, right?
yeah,
From the process, you try to put some nature, some try to study the nature of that process, and you get an equation. So you usually don't know
yeah,
the function, right? So usually the function is implicit. Function is implicit. So you just get an example quickly, but function is implicit. And the second is that the contests might give us a wrong idea that answer is always fx equals to x usually, but in general, the functions may not have a closed form. Function may not have a closed form. Means that it may not even be possible to write the formula for the function explicitly. Okay, and
yeah,
so in that case, functional equation is a necessity. Okay,
yeah,
so these are the kind of things that we have. So let's just try to see one example of a functional equation, and then we just move into actually the tricks and so on, which is what we have to do in the end. We don't want all this philosophy maybe, but yeah, let's try to form functional. Can you give an example of a process using from where you end up with a functional equation, right? uh, Forming a functional
um
equation.
no, I don't
No.
really.
Okay.
Mm.
Yeah, so this is, I mean, if you think about it, any process you take, you will get a functional equation, right? So I mean, if you're taking, let's say, time, and time, and then you take acceleration as a function of time, and then when you multiply with that with the mass, then you adjust the units, and this is the force,
Yeah,
right? This is like a functional equation, right? But of course, this is like a not a good example. So, well, a better example could be, so let's say that this graph is given, okay? Maybe draw a better one like this. So, do you know function fx equals to e to the power x? Must have heard of this function.
yeah, I've heard of it.
You've heard, yeah, you may not have done the calculus. Have you done calculus?
No, I've not done
No, yeah, that's
calculus.
fine. Yeah, that's okay. But you must have heard of this function, right? Now,
Yeah,
this function, this e is really a mystery here, yeah? We don't really know what that is too much. But let's say if someone told you that they plotted the graph of something, and at the point x comma y on the graph, the slope was equal to the value of the function. Slope equal to the value of the function. Meaning that you could state this like something is growing, and the rate of growth at any point is equal to the height at that point. Okay,
yeah,
value for the function. This is an example of studying the nature of the process, right? And setting up you already have an equation. You have to just now write it mathematically, right? Now the slope is also a function of x, right? At every point you get a new slope. That's also a function of x. And in fact, it's a very, very good function of x. That's called the derivative of x. But never mind, it is a function of x. Let's just call it g of x. And the value of the function is fx. There you go. This is the functional equation. And of course, if you
Yeah.
do more calculus, you see that this gx is equal to indeed f dashed x. So you get, this is a differential equation. Okay, let's give me 1 minute. I'll bring my charger. Okay, it's running out of
Yeah.
battery. Okay. Yes. Right. So we are seeing that functional equations come out very naturally. Let's also see another example. Okay. Let's say that there is, days. So we have this day one, day two, and so you're analyzing a certain process on a daily basis, or let's say monthly basis, rather be better. And this is something which you might have seen before. Okay, month three, month four, and so on. Okay, and we have rabbits. Okay, population of rabbit. Let's say that on day one we have 2 rabbits.
Yeah.
Okay, so the number of rabbits. Okay, just 1 second. There is a current issue. ठीक है ना? Yes. Okay. So yeah, now the number of rabbits on the ith day, number of rabbits on day I, okay, is equal to the number of rabbits on day I minus 1 plus the number of rabbits on day I minus 2.
Yeah.
Okay, now this is stated in a more complicated way. Sometimes, like the rabbits in day I minus 1 can reproduce, and so each of them produce equal I minus 2 things, and so this is the increase and so on. But I'm just putting it in a simple way. Okay, so do you see this is also now a functional equation, right? Number of rabbits on ith day, if you call that f of I, then we have this equation.
Yeah.
But this is of a very different nature. This is something which is will not study in the functional equation course. This is done in combinatorial reconciliation. And even the
Yeah.
equation I gave you earlier was a differential equation. So that's done. But those are more specific equations. We have specific techniques to study them. However, we will dealing with um, those ones which don't fall in any category. Okay. So I mean, at least at our level, we don't know what category they fall in right now. Something like this, where nothing is told about the function. Okay, it's not told if it's
Yeah.
differentiable or not. And because it doesn't fall in any category is what makes it very good for a contest type of question. Like it makes, you can just use your imagination and do some substitutions and so on. Use some tricks because there is no theory for it. I mean, of course, there is a theory for this one, but yeah. So let's just get started with this. So let's say this is a function
Yeah.
from R to R. Nothing else is given. Since you have not done calculus, I don't want to go into continuity. But yeah, so this is the question. Now, this is functional equation. There's not much theory. So let's try to solve this. Okay. Let's try to know as much as we can about this function. How much can we say about this function? Yes. Yeah. So here I would like you to give some shots here, what you can find out about this function.
Maybe we can try x equal to y or x equal to 0 and y equal to 0, something like that.
Right. So let's try that. So if we try x equal to y, so here is one technique already, that when you are writing this x equal to y, it is found that it is usually in the long run turns out to be better if you write this as, I'll put x equal to y, you write it like this. So you call the first equation as a statement in x comma y. Okay. And then when you're putting some value there, you just record that in this way. Okay, I'm putting x equal to y, so I'm putting
Yeah.
a statement at x comma x. This comes out to be very useful. Okay, but anyways, yeah. So then what do you get? The core thing doesn't change. You get 2 times fx. Okay, very good. So this is one, and I think you said told me one more thing, that was x equal to y equal to 0. So I'll record that as p of 0 comma 0. Okay, this is a very good habit here. And then we get this. So what can we say from here?
Um, the second one implies that f of 0 equal to 1. F of 0 equal to 0.
F of 0 equal to 0. Okay, so
Yeah.
this implies f of 0 is equal to 0. Nice. Okay, so already we have one value. That's important. Okay, now what can we do after this?
We can try just like x equal to 0 and we can let y be y itself.
Okay, let's see. So let's see if that is useful. Mm, no, that's not useful, right? It just gives you fx equals to x. So we discard that, okay? Because we have f of 0 equals to 0. So
Yeah.
that doesn't work. Right. So what do we do?
Maybe x equal to minus y
X equal to minus y. Okay, let's see.
minus y.
Yeah, minus y. So we have this. Okay.
Wait, no. Uh,
No, I have done something. Okay, I have done a mistake here, right? It's x. It's this, right? And so it is 0. So we do
yeah.
have something. We do have something. Can you tell me what this says geometrically? This, so this is not part of the problem, but just that, what does it say? What does this say geometrically? Um,
It's
about the function.
that
So
the function is x equal to y.
no, no, no. From here you cannot say that. Just from here you cannot say that. And in fact, this is not true. There will be many functions which satisfy this, though
Yeah.
x equal to y, x equal to y equal to x is the only good one. But just that if any function satisfies this, then what can you say about that function? And because we will need to learn functions, more about functions simultaneously to do more functional equations, right? But let's see, what does it say? Think about it. You may not have done the functions chapter, that's in class 11, I guess. Class 10 a little bit is there, but anyways, but that's not the point. F of 0
Yeah.
equals to 0 is already here. Now you see, this is saying that if you find the value of f at x, so let's say x is here for any x, and then you find its value at minus x, means symmetrically, on the negative x-axis, then the
Yeah.
value would be negative. It would be the same value, just the negative of that value. So how would the graph look like? Then it is like the function could also be like this, but it would be symmetric about the origin.
Yeah.
You see,
Yeah. It
this is
will
the
go
thing,
through the origin.
right? And so what is, so in this problem it's not useful maybe, but this says that it is enough to study the graph on the positive x side.
Yeah.
That is the thing, because sometimes that may be useful. Okay, not in this question. This question is probably not in that direction, but anyways, we'll see. So we have to make, and this is, by the way, this is called an odd function, and these are very essential, because once we do more theory of functions, we will see that every function can be written as a sum of an odd and an even function. So these are very powerful
Yeah.
functions. Okay, but anyways, not maybe not useful here. Okay, then what do we do next? We have tried substituting all kinds of things, right? This is probably the most first technique. But at this point, what do we do now? Okay. So we have found, so now we have to be more specific. What I mean, that when you're just
Yeah.
substituting values, you're not getting anything. I mean, you've got something. Now try to be more specific in the sense that try to find some values. I'm not saying it will be successful, but try to find. So try to be more specific and try to find maybe f of 1 or f of 2 or something like that.
Yeah.
So with that in mind, let's see if we can actually find it. So if you put x equal to 1, because that's naturally what you're going to do, then what you're going to get is this 2 times f of 1. Okay. But can I do anything else? Can I substitute 1 and 0? I will not get anything, as we already tried once. X comma 0 is not giving anything. But we have this.
Yeah.
We have f of 2 equals to f of 1. Okay. What should we do from here now?
Um, maybe try to find the relation between f of 1 and f of 0.
F of
So x equal to 0 and y equal to 1.
Yeah, but you see,
Okay, yeah,
that will not work. We already did that, right? We
yeah,
already did x comma 0. Yeah, so we have to be very, that's why
yeah,
recording it like this, maybe I should have not erased that actually. Yeah. Okay. Yes. So that's not going to be helpful. Right. So this seems like a roadblock, right? It seems like it's a block, right? So for these kind of questions where the domain is real, okay, sometimes if they just give you domain natural, then it's very good. Then it will be more obvious that you have to do what you have to do, which I'll suggest right now. But if you're not able to move forward, try to at least find the function on a certain domain. Maybe let's just find it on natural numbers. Okay,
yeah,
let's just try to find it on natural numbers. So that's what we'll try to do. We'll try to find what f of n is. Okay, that's cool. But more than that, which I think we have missed altogether, is let's guess some answers. Right? What are the possibilities that you can guess? That's the most important thing in functional equations. Okay, what possible functions can you think of that satisfy this? I'm not saying you will get an exhaustive answer,
yeah,
but
yeah,
whatever you can think of, that is most helpful, because all our approaches will be guided by that guess. Okay. So I think you already
x equal,
told me. Yes, please
yeah,
say.
x equal to y.
Absolutely, yeah, fx equals to x, right? Uh,
Yeah,
yeah, I mean this fx equals to x. This is the guess. But can we be, uh, can you say anything more? That is very important. This is the most is easiest solution, but can you say anything more than this?
and we can also say f of x equal to minus x.
Absolutely, fx equals to minus x will work. In fact, I'm just speeding it a little bit, okay? But yeah, in fact, if you think about it, you will also see the same thing, maybe, hopefully, that fx equals to cx works for any c, right? For any c, this will work.
Yeah,
You can, yeah. So these are called linear functions, and these form the heart of something called linear algebra, which of course we will not do. The linear algebra is very important in maybe in the harder INMO questions, okay? But yeah, anyways, they are done usually in the camps, okay? But anyways, okay, no, sorry, this is called a linear function because it kind of gels very well with the addition, right? It says that you want to add two numbers and find the value. No, you first find the value and then add. Okay, so it's kind of,
yeah,
yeah, it preserves the additive structure and so on. But anyways, it's called a linear function. Okay, and even the graph you can see fx equals to cx is a linear graph. This will be a line. So all values of this will satisfy. Very important to make this guess. Okay, because now you can immediately see that there is no hope of finding f of 1. It's not possible to find it. It's not even possible. There is no fixed value of f of 1, right? It will really,
yeah,
it can be anything. So we will take f of 1 as given. We'll say that f of 1 is f of 1, and based on that we'll do. So we will try to show, right, because since we have made our guess, we will try to show that for, so we won't directly go to the reals. In fact, we cannot go. Okay, so we will try to show that for all naturals, at least can you show that this holds for all naturals. Yeah, so this is again the steps. Yeah, we do it for naturals, then we'll see. Yeah. Yes. So I mean, we have already shown it for 2, right? F of 2 is
Yeah.
2 times f of 1. How do you show this for all naturals?
Um,
Or at least try showing it for the next few values. Just think. Try for f of 3, maybe.
yeah.
Okay. So now we have a specific goal. We have 3 that we are looking at. So
Yeah.
how can you get what substitution? You can just think of the substitution to make. And I'm sure you can do
Yeah.
that.
That's
Yes. Yeah. Okay.
so. X is 1 and Y is 2. We can do
Absolutely.
that.
Yes. 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 Right. Exactly. You can just put anyway because we know all for the smaller, right? So yeah. So you put it anyhow, and you will see that you get it. So it's really there are a lot of ways to the answer. Okay, to this
Yeah.
easy one. We have this. Now prove it. Prove it in general that this will be true. Because like now you are almost sure, I know, but if you're writing it, because we are giving Olympiad, you have to write the proof. So how do you convince
Yeah.
them that it will hold for all naturals? Okay. So the term that we use for that, mathematical induction,
Induction. Yeah.
have you applied this earlier anywhere, other places?
Yeah.
Okay.
Induction.
Can you describe what this is? Just in your own way. Yeah. Whatever.
So like we have a base case, and then we try to prove that we, we try to prove that we can like sort of um
Mm-hmm.
like infinitely just prove it. So we can
Huh.
do something like f of n plus 1 is equal to f of um
Right.
yeah,
Yeah.
something like that.
No, you're right. Yeah.
And
So basically, you're trying to prove an infinite set of statements,
yeah.
isn't it? And you're assuming for small values it's holding, and you'll prove for the bigger value from there. Roughly, that's what
Yeah.
it is. Though it's a very deep thing. Mathematical induction is one of the axioms and so on, but we will not go into that. All that point is that you're proving. So you have an infinite set of statements, and you've proved it. Let's say, I mean, so I'll say that P is a general statement. It could be any statement. Let's say you prove till P of K. Okay,
Yeah.
so the base case could be K cases. Okay, but the most important thing is that other thing you prove is that if P of K is true, or if the statement holds for K, then P of K plus 1 is true. This is something which you have to also prove, right? In induction, we assume, like, this is in loose language, it is said as you assume that the kth case is true and you prove the K plus 1th case.
Yeah.
Right. And then it will be done for all natural numbers because it just moves forward. It's very obvious. It's obvious,
Yeah.
but it has to be put as an axiom, right? So in if you but yeah, that's not important for us. Let's use it. Let's use. So you assume. So what I can tell you, maybe just as a, you assume this and try to show the next one. So yeah, as probably you're already doing that. Yeah. try to show this. So yeah, you assume for n and try to show for n plus 1.
Yeah. So we can take the base case of uh, f f of 2 equal to 2 times f of 1.
Yeah, the
So
base
x
case is
equal to
fine.
1 and y is equal to 1. And
Yeah.
then
So this is we are
for
assuming hypothesis. Yes, please
yeah.
say. So think of it like this is already given to you, and you want to comment on f of n plus 1, right? Just don't even think of this.
Yeah.
Just think of you want to comment on on f of n plus 1. How are you going to use f of n to do it?
Yeah. So if we substitute n plus 1 into the first one, then you just get f of n plus 1 is equal to n plus 1 times f of 1.
Oh no 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 no. Okay, so I'm sorry. So I so this is true for only a particular n. I mean, so we are assuming that it is true. I mean, otherwise it's trivial, right?
Yeah.
Yeah. So I'm sorry. Yeah, I think the way I wrote it. Yeah. So we assume it for a particular n and show for n plus 1. Otherwise, there's no content in it, right?
Yeah.
Yeah. Right. So yes, just think about it very freely, just in the flexible. So you have to just prove something for n plus 1, right? And you have your information for n. So you just use this equation, right, to break it down.
Yeah.
So f of n you can take it to be x, and you can take this if you want. Simple. And now you use the values. Now you use what is given. So this is n times f of 1 and f of 1, right? Because here we are using this f of n equal to n times f
Yeah.
of 1. And now we are done,
Yeah.
right? Now we are able to
Yeah.
show this for n plus. The induction is a very powerful tool, because the entire process might be complicated, but every step may be simple to see. And that's where you can use your
Yeah.
inductions, right? So very good. So yes, so now we can write that this is true for all natural numbers. Okay. So now we have done one problem. You could say problem was, for all naturals, then it's done. But usually the problems are more difficult than this. So we have shown that for all natural numbers. What should be our next step? How should we move forward? So if the question was for all reals to reals.
Maybe all integers.
Very good. Yes, all integers. Yeah. So nice. Yeah. So how are you going to do that? So now, for example, how are you going to show that f of minus 1 is minus of f of 1? Something like this. Yeah. So I mean, show this. So we are expanding our domain. Okay. Yes.
Um.
So you can again choose some smart values,
Yeah.
right?
X is 0 and y is minus 1.
Exactly. You can do that. But I will say don't do that. I'm saying that there's a better way, in the sense that we have this equation, you remember, f of x equals to minus of f of minus of f of
Yeah.
minus x. We can use this directly, right?
Yeah.
So if the values were like this on the positive side, 1 times f of the negative like this, and so we have it, right? So what I mean is, if you want f of minus n, then just use this equation. It's minus of f of n, and that is
Yeah.
minus of n times f of 1. So we get it in one shot. So this is like they help you to build the function. Okay. So now in fact, we can write that it's true for all integers. I'm just removing these things just to create space. What should we do next?
You can then just jump into rational numbers.
Okay, yeah. Now that is the good part, yeah. So now how do you show for all rationals? Show that. So I'll just be more explicit here, okay, so that we can use the symbols to our advantage. We want to show something like this now. Who knows how to do this? This is a sort of a leap. Yeah. And if we just
Yeah.
focus on positive rationals, the negative rationals will work in the same way. In fact, if we just focus on the positive side only. Hmm. So this we cannot use induction directly, right?
Yeah.
Because there is no next rational number, right? There is no
Yeah.
next rational number. So how do you do this kind of thing? This is
Um.
okay. So you can also think of just proving it for again a yet simpler case for this kind of rational numbers.
Yeah.
You can maybe try for this only.
Um.
Yeah, so it seems like what we have done till now is not very useful for this because we don't have f of 1 by something kind information. We don't have that kind of information. Yeah.
Yeah.
So then how are we going to do this one? That is a problem. So you can try to use the value of 1 and you have to relate 1 by q and 1 somehow. You can go by that. Okay. Or but you have to do something more general. You have to go back to your equation and do something more general for this. Just this will not work. There is no way from here. So, well, one thing that you can do is you can see that these kind of things usually, if they hold for two values, they will hold for more than two or for any number of values. So, let's say if I propose you this statement, so there are other ways to do this also, I believe. Yeah, I think there are. Yeah. But do you think this would also be true for three values?
Yeah.
Yes, it's easy to prove,
Yeah.
right? I'll leave that for you. So, in fact, not just three, for any n, right? You can in fact show this thing for any n. So if it's linear, you can take two steps at a time and you can show that it's true for all n.
Yeah.
So yeah, see, not always the solutions of a functional equation will be this big. This is like one of the central equations which we reduce so many equations to. Usually a functional equation problem would be you take a problem and you reduce this to this kind of problem and then conclude, okay, because solutions of this is like, okay. So usually it will not be so, and of course we are learning the techniques and so it will take less time. Usually
Yeah.
I don't want to get the impression that all functional equations you have to do all kinds of analysis like this. Okay. Yeah. So this is what it is. Now, how are you going to use this to break down the one? And how do you relate the one and the q? So the way I see it is you relate the one and the q by taking the q copies of one by q, right? This is
Yeah.
f of one. And then nobody is stopping me from writing it like this. So I can just write this. So can you finish it off from here?
Yeah. So f of 1 is equal to q times f of 1 by q.
Yes, right. So f of 1 is equal to uh, q times f of 1 over q, right? Which is exactly what we wanted to show. Okay. A slightly, I think, more traditional way to do it is they don't go into this n. They just prove a more generalized version of this, which is equally easy to show. In the
Yeah.
beginning, we could have just done like x here. So we can just in fact show that f of nx is equal to nx times f of 1 and then you can choose your favorite value of x to finish the problem, right? And n,
Yeah.
you can play with those values. You can put n equal to 1 and s equal to 1 by q, and you can get the answer. This There are other ways to do it. I'm just saying that it's a more flex. It's not This is not the only way. Okay, but let's see. So now this is also there in our kit. Yeah. So now how do we show it for all rationals? How do we show it for this p times? Or maybe you can just think of how to show it for 2, right? So I'm just trying to say that it should build from the easier values. Okay. So yes, how do you show this? I mean, yeah.
Um,
So it's very similar to the integer thing, right? We did it for 1, like we did for 1 by q. Now we're just trying to do it for 2 by q. Right? So yeah, so you can use a linearity maybe to split the 2 by q into what? I think.
into 1 by q plus 1 by q.
Yes, yes, absolutely, yes, right. And then you get it, yeah. So now
Yeah.
just use the linearity. So yeah, the linearity, if you think in that terms, then you just have to prove everything for 1, and then from there you can
Yeah.
grow forward, okay? And then you're done, right? And now I won't even bother. Like you can prove that it's true for all p by q, I guess.
Yeah.
So very good, yeah. So we have it for all rationals. Now the question is, how do you prove it for all reals? And the answer is you cannot, because it's not even true. Okay. So it's not true. So from here it one may want it very badly, but it's not true. It is not true that f of x equals to x times f of 1 for all real. It's not true. But under mild
Yeah.
conditions it is true. But I don't want to do that right now, because you may have you done continuity? Mm,
I don't think so.
no, right? Yeah. So I would rather do it. If I do it, I'll rather do it after I introduce that, so that you catch it in a good way, in a useful way. Otherwise I can just say, but
Yeah.
it will not be very useful. Yeah. So it's not always true, but under some mild conditions it turns out to be true. So then the question is, what are all the solutions? What are all the functions? Like I just didn't find the answer then in the end, and the answer is yes, I did not, and I cannot. It's a very hard question to find all solutions of fx equals to x. Sorry, I mean, sorry, finding all solutions to this. Okay. So
Yeah.
yes, that is really hard, because what you have to kind of do is you take this reals and you take the rationals. Okay. Then you take any bunch. In fact, you take any bunch of real numbers. That's like you take pi e, some very nasty numbers, e root over e or something. And what you can in fact do, you can send them anywhere. You can actually, by this function, you can send pi to e, you can send e to root over e, and you can send root over e to pi.
Yeah.
And using this three also, you can build up your function. How? Because now if you have a real number, let's say, which is a combination of these e's, and though this will not be sufficient to form all real, from the root 2 you cannot make by these combinations. If you use rationals here, if you use rationals in these boxes, then we have seen that for rationals we can split it just like this. You can do it for all. You can pull out the rational. That's all I'm trying to say. Just like you could pull out the integer here, you can pull out the
Yeah.
rationals and you can actually get a function. Okay. So yeah, you can see this. It's an impossible task to answer. Basically, any set of irrational numbers that you can take and build the reals from there, you can get your answer. And this is called Hamel basis. But now this is something that we can't discuss at this point, and we don't need to. Okay.
Yeah.
Yeah, we don't need to. Why Hamel basis exists, and that's it goes on to very interesting mathematics. We have to define size of an infinite set, several kinds of infinity, and so on. Yeah, that's the point. And so, by the way, this functional equation has a name. It is called the Cauchy functional equation. So this is the first example in almost any functional
Yeah.
equation book or whatever you see. So yes. So now there will be many other equations. If they look similar, you can reduce them to this. So that's the second technique. Reduction, maybe I should say, reducing a problem to another problem. And that's really basis for a lot of what theoretical computer science people also try to do. We try to do.
Yeah.
So, like for example, let's say if I take yeah, so let's say if I take a different example, so you can just take anything actually. So you can take uh, this this example. So I should not even say F here. I should say take G. Okay. So yeah. So of course the contest questions will usually not look like this, but they can be reduced. Okay. But right now I'm just trying to show a different technique, that is reduction. Okay. So reducing to a central question. Okay, now let's see. So at this point, let's just assume that our solutions to this is fx equals to x times f of 1. Okay, it is true
Yeah.
under continuity and other mild conditions like monotonicity and so on. But let's assume that this is a given. Then how do you solve this question? Using this, you don't want to again independently do that same kind of analysis. Okay, we want to do it by using the theory we have built. Okay, so how are you going to reduce this equation to that equation? That's my question. And domain you can just take to be positive reals.
Yeah. Um, Maybe like the same thing we did as before. So like x equal to y equal to 1.
Yeah, no. That's right. That you can do that. Yeah, and you will succeed. So you can do that substitution. So substitution, induction, and so on, and you will succeed. You will get an answer. But I want to. This is a special strategy. Like I've just observed this over the years, that you can actually reduce this directly to this equation by some kind of manipulation.
Um,
So you can basically, I'm trying to say that to be more precise, a little more precise, is that I want to convert this into addition.
yeah.
Yeah, and maybe also you can start by guessing the answers to this again. So guess and convert the multiplication to addition, or you can try either of them, both of them. So what, try to guess what function looks like this, what function looks like this. Try to guess some identity or guess some, what rule does this look like.
We can just
So don't even
substitute.
think of it like a functional equation question. Just think, what
Yeah.
function does this look like? Let's say you had just
Um,
30 seconds to answer, you have to guess one function.
f of x equal to x squared.
No, that is not like this, right? So you can check it, right? X plus y whole
Yeah.
square is not this, no. So just think, like talk to the function, think of it like that, right? So it is taking a number, and you are adding it and then applying the function. Okay, so addition is turning into multiplication. It's going to grow really fast.
Yeah.
So what is that? The index rule. The index, you think about the index rule that you've learned in high school. This is exactly like that. Hmm? So if gx was 2 to the power x, for example, then this
Yeah.
would work. That's what indices do, right? When you multiply the numbers, the indices add. Addition gets converted into multiplication gets converted into addition in the powers. So that's
Yeah.
your guess. And this can, because your guess will guide you. If you don't guess it, then it will be, you don't know what, because there's no theory for functional equations, because these are just general functions. The functions are nothing. Function is just you have one set and one set, and you can do any type of matching. Right? Who knows what you
Yeah.
can do? There are n to the power m functions if you have done counting. So, anyways, so that's the thing, right? So this is your guess, and of course this is not the only answer. You can take 3 to the power x, it will also work, right? But the idea is that answer is like this. Okay, bit like
Yeah.
this. Now how do we convert this kind of function to this kind of linear function? Or how do you convert this multiplication into addition? What does that for you? That is the log function, right?
Yeah, it
This is
does.
the yeah, that's a log function. So either from the guess you can see, or if you just want to go symbolically, like symbolically, I want to convert this into additions. You have to just talk to it, okay? And you can take log. Now if you say that it can be negative, how will I take the log? Yeah, all that constraints are there, but keeping them, assuming that we're just doing it for positive for the time being, okay? So gx is positive. Now that's something when you're taking the log, then you have to be responsible for this, right? Gx has to be
Yeah.
positive, because for negative, okay, negative also log is defined, but for not for us right now, maybe if I've not done complex numbers, then no. So assume that gx is positive. Now you can prove that gx is positive. That I will leave to you. You can prove it roughly, more or less. Okay, you can put x equal to y and something you can show. But once you do that, and even if you don't do that, we can go to the next step, maybe, because we have to get into the solving. So now you see, so log gy, to work on my presentation. Yes. Okay, now this looks a lot like that equation. So remember, the first step implies this. Okay, that is also important thing in functional equations. We'll see we get extra solutions and you have to check and so on. But for the time being, the first step implies this. Now you see this looks very much like this equation, right? Two things added here
Yeah.
inside the function and then added later. So what should be your new function that will convert this problem to exactly that problem, to our first problem? Yep.
Um. So like log g of x equal to 2 to the power of x, log 2 to the power of x.
Right. Absolutely, yeah. So log g of x, sorry, I just got a mail from my professor. Yeah, sorry. So log g you can take as h. Very good. And there you go. We didn't have to do anything, right? We can now just say that hx is the Cauchy functional equation and its solution is this. Under most conditions, it is this. I'm quite sure in
Yeah.
our exams. So it is this. So you can just say that hx is equal to x times f of 1, and you can work your way back from there,
Yeah.
right? So you hx is what was hx log gx, yeah, sorry. So log gx is this, and you understand now. You can find gx is whatever e to the power x, so e to the power f of 1, and f of 1 will be given in the question. If it's not given, then your answer is just this. Okay, something like that. You see, this is another technique. Okay, so I'm just trying to show the different techniques. Reduction, we don't have to always go through the analysis. And now there are a
Yeah.
whole bunch of questions which can be reduced to Cauchy functional equation, and but of course we will not discuss them in the class. That you have to practice, and then we have to discuss the things from there. Okay, so yeah, so that is what I wanted to do in this thing. Now let us just do one more example which is of a slightly different nature, and then
Yeah.
there are so many variations, yeah, that it takes at least 2 3 classes to get the basic variations done. And then also functional equations is that kind of topic, you can't really say much. But anyways,
Yeah.
that's why it's more popular, because they are running out of number theory questions and inequality questions, right? Because there are theories for them. But functional equation and combinatorics is still running well in IMO, right? Because these are so random things.
Yeah.
So yeah, so let's just do one more question. So here maybe the technique can be, yeah, I wanted to say so much more, but let's just do this one. So so function is again from real to real, and here the function is of a slightly different nature. So we have this. So this is square of the function, right? Not composition. Yeah. So this is this. Yes. So yeah, solve. Yes.
So
Hmm.
we can use that f of x plus y is equal to f of x plus f of y and substitute that into the left side.
Oh, no, no, we can't use that because that, no, no, that is not given in this question.
Okay.
Ah, right, right, right. No, no, yeah. So yeah, that is only for that question. Yeah, so all we call
Yeah.
all our functions f because we'll run out of symbols. Yes. So since I mean, so you can just try some random substitutions to start with, right? Or something
Yeah.
like that, yeah. Because really, even I don't know. I mean, if just thinking, yeah, just start with some random substitutions. So yeah, I just put 0 and 0. Yes. Uh, yeah. Okay. First thing is that it's very unlikely that you can reduce this to Cauchy through that thing, right? Because there's a
Yeah.
square, so it's very unlikely that you can do it. But I don't know. You can still maybe do it, but at least it doesn't seem like right now. So just put 0 everywhere, and you will see that as you did earlier. Uh, you will get this, right? So naturally f of 0 is 0, so that is given again. F of 0 is 0.
Yeah.
Now I will suggest that, so I mean, now if you try to put some other combinations, you will see it's not working, because it's just like the Cauchy functional equation case, right? I mean, okay, no, 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 I think I'm wrong. You please think. Sorry, I just rushed that. Just try substitutions. Just think.
Yeah.
So let's just try the other substitutions you made. Yeah. So we can just try something like this. This is what you did in the Cauchy functional equation also, and it was good, right? Because it gave us,
Yeah.
it saved us a lot of work. From the negative side, we didn't have
So
to do. Yes, please say.
so I think here we can like try to prove that f of n squared is equal to n times f of 1 squared.
Um, no, n times f of 1 squared. No, I don't think so. Because think about it, right? This function. Okay, how do you think we can show this? If you're saying so. Uh,
If like because I took like x is equal to 1 and y is equal to 1,
okay, okay,
then
yeah.
I got f of 2 squared equal to 2 f of 1 squared. Then
Oh,
like
yeah,
I
yeah,
did that
yeah. Okay.
again and I got f of 3 squared equal to 3 times f of 1 squared.
Uh, right, right, right. You're in fact. Okay, no, no. So sorry. So I have written it wrong. You're right. Yeah, I've written it wrong here, right? It should be square here. Yes, 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 yes. So I think in this way you can. Yeah, you're right. You can just grow on and you can show this,
Yeah.
right? That's right. So for naturals you get this, but and I guess for rationals also you can get something similar, right? Yeah.
Yeah.
By yeah, so that's good. So you have extended the technique. That means you're really catching it very nicely. Very good. However, look at this equation for a second. This equation. I think we underestimated this. Okay, what will that give you?
Um, that minus f of minus x squared is equal to f of x squared,
Right,
because
but is,
f of x minus x is f of
yeah,
0,
but is that
and that's
possible?
just it.
But is this possible? No, right?
Um,
Can't be
no,
negative.
yeah,
So that means
yeah,
there is no function. Yeah, there is no function from R to R.
yeah,
Very good. No function. Yeah. So the answer is no function from R to R. But we have made some other observations which I had not thought in the beginning, that yeah, if the if it was just naturals to naturals, then maybe, and I'll tell you why it's just a maybe. Because if it's just from naturals to naturals, you may think that you have got an answer here in this form. Yeah.
yeah,
But you think, here is the thing, all our steps is from top to down. Yeah, the top one implies this one, and a top one implies this, that then this implies this, and this implies this, but nobody told us that this must also imply that, and we have to check that.
yeah,
Okay, and if you check that, you, let's see if that is true when you check it. So put it, so if you put n plus m whole square, if you, then you're going to get that as n plus m times f of 1 square. If you have to put in check, I mean, hopefully it is true, and uh, f of n square is equal to n times f of 1 square, right? Yes, it is true, right? It does satisfy, but in general you have to check it. Okay, if it's
yeah,
not, then you can't just say, but yeah, it does work out. Very good. So you see, for naturals to natural, probably you can do. For integers, no, for integers you can't do, right? Integers, this will not be true, because for the same reason, right?